Myself Dr. P.R. Krishnaveni, Associate Professor of Chemistry, Sasi Institute of Technology and Engineering, Tadapalligooda. Welcome to the lecture 4 of Engineering Chemistry course. In lecture 3, we have discussed about graphene and fullerenes. Graphene is nothing but an allotrope of carbon, which is an which contains sp2 hybridized carbon atoms. After that, I had discussed the various applications of graphene and applications of fullerenes. And now coming to the lecture 4, that is on carbon nanotubes. So carbon nanotubes are the long thin cylinders of carbon and were discovered in 1991 by S. Lizima. These are large macromolecules that are unique for their size, shape and remarkable physical properties. Carbon nanotubes are allotropes of carbon with nanostructure having length to diameter ratio greater than 1 lakh to 1. Nanotubes are members of fullerene structure family. So they are considered as a sheet of graphite, a hexagonal lattice of carbon rolled into a cylinder. Thus carbon tubes are extended tubes of rolled graphene sheet. That means we will take a graphene sheet. When that graphene sheet is rolled, it will be converted into a single walled carbon nanotube. Coming to the types of carbon nanotubes. Carbon nanotubes are lattice of carbon atoms having each carbon is covalently bonded to the other carbon atoms. And that coming to the types of the carbon nanotubes, single walled carbon nanotubes and multi-walled carbon nanotubes. These single walled carbon nanotubes are formed by rolling the graphene sheet. So this is how the single walled carbon nanotube is formed. That means they contain single layer of graphene sheet and they will have greater tendency to align as ordered bundles. They will have greater tendency to align as ordered bundles. And these single walled carbon nanotubes are mainly used to study the properties of the nanotubes. And multi-walled carbon nanotubes. These multi-walled carbon nanotubes are formed by rolling the graphene 2 to 3 times or more times. That means this contains 2 or more layers of carbon. That means graphene sheet. See, this is how it is appearing. And this will form unordered clumps. Whereas with single walled carbon nanotubes we will be getting ordered bundles. So coming to the single walled carbon nanotubes, they have a diameter of close to 1 mm with a tube length that can be many millions of times longer. The structure of the single walled carbon nanotube can be obtained by wrapping a 1 atom thick layer of graphite, nothing but what? Graphene, into a seamless cylinder. And there are 3 types of single walled carbon nanotubes basing on the way how the graphene sheet is wrapped. So graphene sheet is represented by a pair of indices Nm called chiral vectors. So basing on this, the single walled carbon nanotubes can be classified as zigzag carbon nanotubes, armchair, and chiral carbon nanotubes. So here I have said, no, there are three types of single wall carbon nanotubes: zigzag, armchair, chiral nanotubes. So this zigzag type of nanotubes will form when m is equal to 0. These are here, n and m denotes the number of unit vectors along the directions. And armchair type will be formed when n is equal to m. And this chiral will form when n not equal to m. So this is how we will show the structures: zigzag, armchair, chiral. This you can clearly see in this picture. See here, types of carbon nanotubes with respect to rolling direction of the graphene sheet. So with respect to the direction of the rolling sheet, you will be getting this type of structures. So before rolling, so zigzag means what I have said, this will occur when m is equal to 0. Here the lines of the carbon bonds will be down. See here, these are the lines of the carbon bonds. These are lying down. And coming to the armchair, this armchair structure is possible when n is equal to m. Here the lines of the hexagons will be parallel to the axis of the nanotubes. And this chiral is possible when n not equal to m. Here twisting of the bonds will be taking place. Coming to multi-walled carbon nanotubes, there are two models which can be used to describe the structure of multi-walled carbon nanotubes: the Russian doll mode and the parchment model. In Russian doll mode, the sheets of the graphite are arranged in concentric cylinders. And coming to parchment model, a single sheet of graphite is rolled around itself, resembling a scroll of parchment or a rolled newspaper. So this is how the multi-walled carbon nanotubes are visible. See here, they are appearing like a rolled newspaper. Next, coming to the preparation of carbon nanotubes. We can prepare carbon nanotubes using three methods. First one is arc discharge method. Second one using laser ablation method. And third one using chemical vapor deposition method. So these are the three methods we will be using. Mainly these three methods will be used for the preparation of carbon nanotubes. Coming to the first method, arc discharge method. This method is mainly used to prepare C60 fullerenes. Here it consists of two carbon rods placed end to end. One will be acting as anode and the other one will act as cathode. And these will be kept in an enclosure. Usually that is filled with an inert gas. And here this is connected for providing the direct current source. So coming to this method, here the C60 fullerenes are prepared through arc vaporization of two carbon rods placed end to end, separated by 1 mm in an enclosure. So this is called as the enclosure. This enclosure is usually filled with inert gas like helium, and it is maintained at a pressure of 50 to 70 MBR. A direct current of 50 to 100 amperes will be driven between the electrodes. So this discharge will vaporize one of the carbon rod and forms a shaped deposit on the other electrode. So this is the deposit which is formed with the vaporization of one of the carbon rod. So this will form the shaped deposit on the other one. Here the yield depends on the uniformity of the arc as well as the temperature of the deposit on the other electrode. Second method is laser ablation method. This method is mainly used to prepare single walled carbon nanotubes. Here they will be taking a laser. This is the graphite target. It will be placed in an oven or furnace which is maintained at 1200 degrees centigrade, and this is the copper collector, that means which acts as a catalyst here. Here a pulsed laser will be used to vaporize the graphite target. Here this is usually placed in an oven which is maintained at 1200 degrees centigrade, and it is filled with inert gas argon, and this is maintained at a pressure of 500 torr. As a result, this graphite target will start vaporizing. It expands and this will be cooled. So now the copper collector, it will go into this expanded graphite tubes, preventing it into close like a case-like structure, so that the tubular molecules will grow into single walled carbon nanotubes. Next, third method. Third one is chemical vapor deposition method. In this method, they will be taking a carbon source, and this carbon source will be taken in gaseous phase, and a plasma source for transferring energy to this gaseous carbon source. The commonly used carbon sources are methane or acetylene. So this plasma will transfer energy to this gaseous carbon source, and it will crack this gaseous carbon source into atomic carbon. Now this atomic carbon will move towards the substrate. This is the substrate which is coated with a catalyst. This substrate will be heated, and the coming carbon source will react with the substrate and forms the carbon nanotube. Next, properties of nanomaterials. The important properties of the nanomaterials are mechanical properties, electrical properties, vibrational properties, and catalytic properties. Mechanical properties means tensile strength. Nanomaterials will have high tensile strength. They are hard and they possess elasticity. Coming to the electrical properties. Electrical properties, how we can say means, here they show conductivity from semi-conductivity to superconductivity. Basing on the size and chirality of the molecule. Instead of saying size, it is better to say diameter. And chirality of the molecule. Next, vibrational properties. The carbon atoms in the carbon nanotubes are capable of moving to and fro. As a result, two modes of vibrations are possible. A1G mode and T2G mode. A1G mode means here in and out oscillation of the tubes takes place. T2G mode means here squashing of atoms takes place or squashing of tubes. That means oscillation between a sphere and an ellipse. Next, catalytic properties. Nanomaterials prepared of transition metal oxides. Nanomaterials prepared from transition metal oxides. They act as good catalysts. And the catalysis can be further enhanced using nano-sized gold and platinum. Catalysis can be further enhanced using nano-sized gold and platinum. Next, applications of nanomaterials. Especially here I will discuss the applications related to nanotubes. These nanotubes are useful in killing cancer cells. How means? They will be designing a device which is capable of identifying the affected cancer cells. Why means? This device would contain a small computer and large number of binding sites so that the drug will be delivered to the affected cell and it kills the affected cancer cell. And providing oxygen. In general, the tissue damage is due to the inadequate supply of water. Tissue damage. It is due to inadequate supply of oxygen. So we can supply oxygen adequately despite red blood cells by preparing the artificial red blood cells using nanotubes. And drug delivery. If a drug is prepared in nano size, it increases the solubility as well as it is easily absorbed. Next, nanotubes also finds application in aerospace. Why means? aircraft components, they are striving for the manufacturing of the components which are strong, tough and long lasting. The aircraft components prepared by nanomaterials are strong, tough, efficient, fly fastly, can tolerate high temperature. And next application is high energy density batteries. Ordinary conventional batteries, they require frequent charging, and the batteries prepared by nanomaterial nickel and metal hydride batteries. They require less frequent charging and they will enhance the physical and chemical properties. And they also find application in high definition television. In general, the resolution of a picture depends on the size of the pixel. Resolution of the television depends on pixel. The pixel is usually made with phosphorus, and resolution decreases with increase in size of pixel. So that's why if we prepare the pixels with lead sulfide, nanomaterial lead sulfide, zinc sulfide or lead telluride, which are prepared by sol gel method, will increase the resolution of the television. So these are some of the important applications of nanotubes. Thank you.